The first topic I would like to introduce about Newton's mechanics are the axioms of Newtonian mechanics. And when you look at the literature, you will again find slightly different ways of introducing and formulating these axioms. They have evolved since Newton originally formulated them. And I would like to present them in the following form. There are 3 basic axioms, and then there are a number of additional assumptions that are usually made that are not labeled axioms, but that in many introductions and applications of classical mechanics are made in addition to the conventional Newtonian axioms. One of the reasons why I decided to start this course on classical mechanics with discussing space and time and Galileo transformations, Galilean invariance, is that I hope that some of the axioms of Newtonian mechanics will be more plausible to you, knowing what we have already learned about space and time. So, the first axiom is in a way very simple. Remember what we learned in the previous chapter, that one of the consequences of Galilean invariance is that whenever we have a time-independent reference frame, then, and this was one of the problems on your first problem set, then you prove that the only dynamics that is Galilean invariant of a single body is that it moves uniformly. So a consequence of Galilean invariance is that in a time-independent reference frame, a single body, that is a body which is far removed from all other bodies, must necessarily move uniformly. The key idea of the first axiom is to say, is basically an inversion of this argument. Namely, that you recognize a time-independent reference frame by the fact that a single body, which is far removed from all other bodies, moves uniformly. Such a time-independent reference frame is also called an inertial frame. And the first axiom simply says such inertial frames exist. So it says, on the one hand, it says that such frames exist, and you recognize them by the fact that in these frames a single body moves uniformly. The second axiom requires a little bit more space to describe. And it has, in a way, separate parts. The first part talks about mass and momentum. You all know, of course, that every mechanical body has a property called mass. Every object has a mass. This is an experience from everyday life, and you've known that for a long time. But if you think about it, it's a non-trivial statement to say that every body has an invariant property called the mass. So let's write this down explicitly. So the first statement is that every mechanical body is endowed with an invariant property called the mass. And it's usually denoted by an M. In addition, every mechanical body that moves around in space at a certain velocity has associated with it a momentum. So every mechanical body also has a so-called momentum, and this momentum is defined as mass times velocity. So this is not always sort of stated explicitly as an axiom, but it's certainly an assumption that is made explicitly or implicitly. So not only does every body have a mass and a momentum, but furthermore, you can add them up. That's also a non-trivial statement. So when you have a body number 1 with mass m1 and momentum p1, and you have another body with mass m2 and momentum p2, then you can look at the two objects together, and certainly when you look from far away, you can treat that like a single object, in many respects like a single object, which has a total mass m1 plus m2 and a total momentum p1 plus p2. So I can treat this like a single body with total mass m1 plus m2 and total momentum p1 plus p2. Okay, so far so good, all very simple. Everybody has a mass, a momentum, and you can add them up. I don't know how you feel about this, but I personally have often wondered why is it that every object has an invariant mass? You can take it as a given, but you can also ask, is there maybe a plausible argument to understand a little better why every object should have a well-defined mass? I don't claim to have a definite answer for this, and this is a very deep question, of course. You've all heard about the Higgs particle and how particles acquire mass, so it's of course a very deep and problem that many people think about. But I'd like to give you sort of a short motivation, maybe to make it a little bit more plausible, why it should be so. So let me try. No guarantee that you'll be convinced, but I'd like to try. So why should every object have a mass? My starting point is what I just said, that when you have two objects and you go far away and you look from afar, then effectively you should be able to treat these two objects together like a single object. Often you have that in the sky, you observe, I don't know, two nearby stars or a star and a planet, and from far away perhaps you cannot even distinguish them very well, and you treat that whole thing as a single object. So let's take this as a starting point, and let's require that from afar two bodies, let's say at positions x1 and x2, can be treated effectively like a single body. At some position which I call capital X. Now the first observation is that by symmetry, this position capital X of this effective single body should lie somewhere on the axis connecting the two bodies. Otherwise, that would be hard to really to justify why it should be anywhere else. So if I have here body 1 at position x1, I have body 2 at position x2, I would expect that my position capital X that describes my effective combined object, I would expect that should lie somewhere on the axis connecting the two. So X on the axis connecting the two bodies. So this would imply that capital X is some linear combination of x1 and x2. That's what I expect. Where these weights, lambda 1, lambda 2, and I indicate this up here with this upper index 1, 2, these weights, they depend on the properties of the two bodies. What else would be reasonable to require? I claim that another reasonable assumption to make is scale invariance. I can look at these two objects on different scales. I can go far away, and then from far away, these two objects, they look very close. So this is from far away, and effectively, this is like looking at two stars that are very far away in the universe, and maybe their distance is below the resolution of our telescope, and then we don't see two objects, but we see just a single object. Okay? So this is from very far away. Then we can zoom in. We can get closer to this object, and zooming in, at first it looks like this, and then as I get even closer, it may look like this. Okay? And reversely, I can zoom out, and then I see the objects closer and closer together. Now, scale invariance says that there is no, in nature, there is no absolute length scales. All distances are relative distances. There's no absolute length scale. And that suggests, if that is the case, then this would suggest that the ratio of the distances between this point capital X and the two single bodies, that the ratio of these distances should be the same, regardless of the scale at which I look at these objects. Yeah? So I would expect that I have the same ratio of distances. Regardless of how much I zoom in or zoom out. And this implies that these coefficients, lambda 1 and lambda 2, they are really constants, they are invariants. Yeah? And they are properties only of the two, they are invariant properties of these two bodies. Yeah? So these are invariant properties of the two bodies. Invariant under a change of scale. What's important to note, however, is that at this point, at least, these lambdas may depend on both bodies, not a single body, but really the two bodies together. So they are invariant properties of the two bodies together, not necessarily individually. Now, we can go one step further. So far we've done that with two bodies, and now we can add a third body. So let's now add a third body. So then we will have here, say, x1, x2, and we'll have a third body, x3. And then we expect, again, with the same logic, when we look from far away, this is effectively, so from afar, this is effectively one body. We should be able to describe that as effectively one body. At some position capital X, which for the same symmetry considerations we expect to be somewhere on the plane spanned by these three particles. And then we require associativity. In the following sense. Here we have three bodies, and from afar we effectively describe that as one body. We can arrive at that effective description also in two steps. We can say I take two of the three bodies, and effectively I describe these two bodies as a single body, and then I take this effective body and the third body, which are again two, and say I describe that as effectively one body. Now, associativity here means that it shouldn't matter how I do this grouping. Whether I first take body number 1 and number 2 together effectively as one body, and then I add body number 3, or I first combine number 1 and number 3 into an effective body, and then I combine that with body number 2. So I try to illustrate that graphically in the following way. I can either first group these into some effective body here, and then I have this effective body and the third one, and combine them into a new effective position. This is equivalent to a different order in which, say, I first group these two into an effective position here, and then these two into an effective position here. Okay, so let me, maybe to make this clearer, in red, this is eventually the effective position of this object comprising all three parts. Okay? Now this requirement implies that if I draw here x1, x2 and x3, and I have somewhere in the middle, here I have my effective position x. Right? This requirement implies the following. That when I first group x1 and x3 together to an effective body, then I get an effective position 1, 3. Here I get an effective position 2, 3, and here an effective position 1, 2. And then I connect, for example, x1, 3 is the, when I group bodies number 1 and number 3 to an effective single body at position x1, 3, and then I group that effective body with x2, and then I get a final effective position capital X, that's the red dot, which must be on the axis connecting the two bodies. So it must lie on this gray line connecting x1, 3 and x2, and the same for all other combinations. And so you see that this effective position of all three bodies, the red dot, must be exactly at the intersection of the three gray lines. Up here I should add this idea that the effective position capital X is in the plane defined by these three bodies, means mathematically that capital X is now a linear combination lambda 1 x1 plus lambda 2 x2 plus lambda 3 x3, where these lambdas depend on properties of all three bodies. 1, 2, 3. Okay, this is for three bodies, and then you can go on and on. You can say, now I add a fourth body and a fifth body, and I iterate. And it must always be possible to arrive at the final effective position of my effective single body iteratively by grouping pairwise two bodies of my collection. So we go on and on. We say the same must work for 4 or more bodies. Now, and we always require this associativity. And this associativity, so it doesn't matter the order in which you group pairs of particles into an effective single body, this associativity is ensured if there exists an invariant mi, which is now associated with the single body I, associated with the single body I, such that this lambda, this weight lambda I, now when we have n particles, is given by mi divided by the sum, j goes from 1 to n over all bodies mj. And this invariant now we call the mass. So you can convince yourself that with this way of calculating the weights lambda, with such a definition, you ensure this associativity. So it doesn't matter how you combine particles into effective mechanical bodies. Now there's a non-trivial question whether this is the only way to ensure associativity, and but this is something I don't want to discuss here. Maybe it will come up as an exercise for you, but this was only intended to make plausible that the fact that there's an invariant property called mass can be, if you believe these various arguments, plausibility arguments that are made, can be reduced to the requirement that we can combine bodies into effective single bodies. So here is the question, is there a way perhaps to motivate this concept of momentum? I mean, velocity, we all know what it is. It's just a change in time of the position. But momentum is perhaps not clear from the beginning why you would need such a quantity. Here again, you might want to start from Galilean invariance. And on the first problem set, you showed that a single body performs a uniform motion if the dynamics is Galilean invariant. A single body must perform uniform motion. Now, if it is indeed true, what I said before the break, that it should be possible to combine several mechanical bodies into an effective single body, then this statement should hold for this effective single body as well. So this must hold for the effective single body too. Now this implies that the acceleration of this effect of the position, also the acceleration of this effective single body, so the second order derivative of its position, which, as we know, is given by this linear combination of the positions of the individual particles, and we said the lambdas are invariant properties, so they don't change in time, and then hence the acceleration of the effective body is a linear combination of the accelerations of the individual bodies. And then we said just before the break, in order to satisfy the associativity requirement, the lambdas must be given by these masses. So we can write the lambdas as 1 over sum of the masses. Times the individual mass mi, and then we have xi double dot, and this in turn we can write as the derivative in time of the sum over I mi xi dot, but this is nothing but the velocity, so we have vi. Now the motion of the effective body must be uniform, so this acceleration, this must be 0. Now what we have in here, this is what is defined as momentum. And when we sum over all the bodies, then we have a total momentum, which is the sum of the individual momenta. And here you see how the concept of momentum arises naturally from the requirement that the motion of the effective body must be uniform. And this in turn follows from Galilean invariance. Let me return to the Newtonian axioms. We were still talking about the second axiom. We were talking about the first part, that there's things called mass and momentum, but the second axiom also says something about the dynamics of the system. The second axiom includes the equation that you all know, that the change in time of momentum equals the force. Whereas we just said the momentum is mass times velocity, and as long as the mass is constant, then then p dot is simply mass times acceleration. Are there situations where the mass is not constant? Yes, for example, when you consider a rocket, which is propelled by emitting mass, then the mass of the rocket is not constant, but we will generally have to deal with situations where bodies have a well-defined and a constant mass. Now, what are the consequences of this second axiom? What can you do with it? First of all, one consequence of the second axiom is that you can use it to measure mass, or at least relative mass. How is that? Consider consider a spring, right? And here you have a mass m1, and then you have another spring. You have the same spring, but then you have mass m2. And you know from Hooke's law, you know the force exerted by the spring. So in both cases, you have here a force F acting on the mass. In the first case, this force leads to an acceleration A1, which is 1 over m1 times this force. In the second case, it leads to an acceleration A2, which is 1 over m2 times the force. Now, from this you know that the ratio of accelerations, so A1 over A2, this equals m2 over m1. So the second axiom enables you, if you know the law of force, and you have two objects of unknown mass, then you simply subject these two objects to the same force. You measure their accelerations, and by taking the ratio of accelerations, you can determine the ratio of their masses. So the second law, the second axiom, enables you to determine relative masses. You can take one specific object and say, I define this object to have to be a reference mass. Like for many decades, the kilogram, the reference kilogram, was stored somewhere in Paris. It's now in a museum in Paris. So this body was once defined to be 1 kilogram. And then with this method, in principle, you can measure the mass of every other object. So, note this. So, you can take a reference body to define the unit of mass. Alright, the first situation was a situation where you knew the law of force and you used that to determine the mass. You can also go the other way around. You can have the situation where you know the mass, maybe you've determined it in a different experiment, but you don't know the law of force. So then you can go the other direction and you can measure the force. So you know the mass, you measure acceleration, and then you determine the force. Very simple. And the third consequence or use of the second axiom is that it gives you the equation of motion for a body. It tells you how a body moves in time. So it gives you the law of dynamics. I should remind you of the principle of determinacy, which says, well, we have here P dot equals force. We know momentum is mass times velocity, and therefore acceleration is 1 over mass times force. The principle of determinacy said that the acceleration is a function of positions and velocities only, and possibly explicitly time only. This implies that forces are functions of positions, velocities, and time only. Let's go to the third axiom of Newtonian mechanics. So, if I have two bodies, body number 1 and body number 2, there are forces between these two bodies. Let's say this is the force exerted by body number 2 on body number 1. And then there is a force exerted by body number 1 on body number 2. And the third axiom says, as you correctly stated, action equals reaction, meaning that, oh sorry, I have here the wrong order of indices, so it's 2, 1. So F2, 1 equals minus F1, 2. Note that this axiom and none of the other axioms necessarily imply that the forces act along the axis connecting the two bodies. So on purpose I drew the force vectors in some arbitrary direction which need not be along this connecting axis. Now, what are important consequences of the third axiom? The third axiom ensures that, well, F21, that is the change of momentum by the second law. This is the change of momentum of the second particle. F12 by the second axiom is the change of momentum of the first particle. So action equal reaction ensures that the sum of the two momenta is actually constant. So that the time derivative of the total momentum vanishes. So this is momentum conservation. And as I tried to argue before, you can say this in turn is equivalent to the requirement that two bodies taken together as an effective single body behave as a single body should behave in an inertial frame, namely move uniformly. Yeah? So the effective single body moves uniformly as required by Galilean invariance. Okay, these are the three traditional axioms of Newtonian mechanics. Just a quick rerun. The first one simply says there are reference frames which are inertial, and they are, you can recognize them by the fact that single bodies that are far away from all other bodies move uniformly. That's number one. Number two says bodies have two properties, namely mass and momentum, and the change of momentum is given by the force, And the third axiom says when you have two bodies acting on each other, exerting forces on each other, then action equals reaction. And this ensures momentum conservation. There are typically, they are not labeled as axioms, but one typically makes at least two additional assumptions. And let me call these supplementary assumptions. One assumption is that when you have two bodies, 1 and 2, then actually the forces act along the axis connecting the two. So this is the assumption that F12, which is equal to minus F21 by the third axiom, that these are parallel to the axis connecting the two bodies. And this should remind you of one of the problems on the last problem set, where you showed that when you have two bodies and you require Galilean invariance, and you assume that the force does not depend on velocity, that then the forces must in fact act along the connecting axis. So this, I hope, makes this supplementary assumption a bit more plausible. Yeah? So here again, see homework problem. A second supplementary assumption that is usually made is the superposition principle. This means the following: if I have many bodies, not only body number 1 and number 2, but I also have body number 3 and so on, so I have n bodies, then the, let's say, body number 2 exerts on body number 1 this force, F12. Body number 3 exerts on body number 1 this force, F13. And so on. Body number n exerts a force F1n. The superposition principle states that the total force, which then determines the dynamics of body number 1, is simply the sum of the individual forces. So there is here a total force, F total, and F total is simply given by the sum over all particles, and then the sum of all the forces acting on particle number 1. Up here I just realized I should just add for completeness that this holds provided there is no dependence on velocity. So the supplementary assumption number 1, for example, does not hold for the Lorentz force. This concludes the axioms of Newtonian mechanics. Now that we've finished the axiomatics, I would like to start solving equations of motion. And we'll start with the simplest case, namely a single mass point. And here's just an overview what you have to do in order to solve the equation of motion. The recipe is as follows. You always have to start with the law of force. So some function f, so the force as a function of position, velocity, time. For example, for an elastic spring, you have Hooke's law, and that means that the force is minus some spring constant times r minus r naught, where r naught is the equilibrium position of your body. Step number 2. Once you have the law of force, you have to solve a differential equation. Namely, the equation mass times velocity times acceleration equals the force, which, as we know, is given by r as a function of position, velocity, and possibly also explicitly on time. This is a second order differential equation. So you get two integration constants. It now depends on the dimensionality. If you have motion in three-dimensional space, then you have 6 integration constants. If you have just motion in one spatial dimension, then you have 2 integration constants. So in general you have 2D integration constants. Now the integration constants can be related to initial conditions. So this is step number 3. You relate the integration constants to initial conditions. i.e. the position at your starting time t0 and your velocity at your starting time t0. Then you have the general mathematical solution of your equation of motion, and then the last step, which as a physicist you shouldn't forget. As a mathematician you are perhaps done at this point, but then you should discuss the solutions. So what are the properties of your solutions? What do they tell you about the physics of the system that you are looking at?